Welcome. Now, we will discuss the second method of speed control, static control of rotor resistance. So, this method of rotor resistance can be controlled only in slip ring induction motor or wound rotor induction motor. Obviously, in squirrel cage induction motor, rotor resistance is fixed, cannot be varied. So, this method of speed control is applicable only to wound rotor induction motor. What is the principle? Let us see. The principle is based on the induction motor speed versus torque characteristics are with variable resistance. So, this graph set of characteristics shows the induction motor speed versus torque for different rotor resistances. The blue line shows the speed versus torque for rotor resistance equal to nominal rotor resistance RR. If resistance is increased by 50%, the characteristic is obtained is green one, and if the resistance is increased by 150% from the nominal value, that is rotor resistance is 2.5 times the nominal rotor resistance, then the graph is the red one, and if it is 3.5 times the nominal rotor resistance, graph is again the blue one, this one. So, what we see from this set of characteristics? With nominal rotor resistance, this is the starting torque. Starting torque is given here. With increased rotor resistance, the starting torque increases. So, as the rotor resistance is increased, starting resistance in the starting torque increases up to a certain value, beyond which again the starting torque also reduces, because maximum torque is not obtained at the start. And another point, the maximum torque for different rotor resistances is constant, but the speed at which the maximum torque occurs changes with rotor resistance. Okay. So, these are the features of speed versus torque characteristics for different rotor resistances. So, now this principle is used for speed control. For example, suppose the load torque is given by this line, load torque is given by this line. So, with rotor resistance RR, speed is given by this point. If 1.5 R, speed is given by second point. With 2.5 R, speed is given by the third point, and with 3.5 R, the speed is given by the fourth point. So, as the starting torque increases, as the resistance increases, for a given torque, the speed reduces. So, this is the principle of speed control with rotor resistance. So, let us understand what are the salient points here, salient features. So, with rotor resistance control, smooth speed control of the motor can be obtained by varying the effective rotor resistance per phase, and maximum torque is independent of rotor resistance. Speed at which maximum torque occurs depends upon the rotor resistance, and for the same torque the speed reduces with increasing rotor resistance. And another point, starting torque increases, that is also advantage. This method is used to increase the starting torque, and main advantage of this rotor resistance control is the torque capability remains same even at low speeds. That you have seen in the criteria, even at low speeds the torque capability is same, and the cost is very less. So, low cost high torque capability at low speeds makes it preferable for cranes and other intermittent load applications. Disadvantage of rotor resistance control method is low efficiency, because in the external resistor additional losses occur, I square R losses. So, efficiency is the poorest in this method. In the conventional method of rotor resistance control, a drum controller is used to vary the three resistances in the three phases simultaneously. or 3 rheostats in rotor circuit connected in star with a single movable jockey is used in the rotor circuit to this is the conventional method. And the conventional method of this vary rotor resistance scheme is replaced by static rotor resistance control scheme. In the static scheme, a diode bridge rectifier, a chopper and one external resistance is used, that you can see in the next slide. So, this is the circuit diagram of rotor resistance control scheme. So, this is the induction motor. So, this is the induction motor, the rotor terminals are marked. So, this is the rotor okay. So, okay. So, the rotor has 3 terminals and stator has also 3 terminals. So, these are the 3 phases you can say A, B and C phases of the stator, and A, B and C phases of the rotor, and extra wire is just shown from the circuit taking a standard symbol for simulation. So, those are removed, and this is the diode bridge rectifier. Diodes are say D1, D3, D5, D4, D6 and D2. This is the 3 phase diode bridge rectifier, and this is the filter. Filter is used to reduce the ripple in the output current and output of the rectifier current, and also to eliminate any discontinuity. So, this is the DC side and DC side current is ID. ID is the DC link current. ID is the DC link current. And the filter has a high inductance LD and maybe a small resistance also may be there RD. And the rotor current is, let us say, I2, I2A, current in phase A. This is the rotor current. So, in this static rotor resistance control scheme, so the diode bridge 3-phase diode bridge rectifier is connected to the rotor terminals, and rotor power is at slip frequency, slip voltage and slip current, current at slip frequency, and that is rectified to DC by the diode bridge rectifier, and then the rectified DC is filtered with the inductor, and a resistance is connected R. This is the external resistance. This external resistance is connected across the DC link, and one chopper is also connected across the DC link. So, when chopper is on, what is resistance between points A and B? Obviously, RAB is 0, because chopper is a switch static either mostly a transistor. So, it has very small on state resistance. So, it is almost 0 resistance when chopper is on. So, RAB effective resistance across AB is 0. When chopper is off, then the switch is open, chopper switch is open, transistor is open. So, resistance between points A and B is RAB equal to R, the external resistance value. So, this way this chopper is switched on and off. You can see the timing diagram. chopper is on for a duration t on and off for a duration t off. This is a t off. So, total time period t is t on plus t off. The chopper is switched on and off periodically, and this varies the effective resistance. Okay. So, this in the diode bridge rectifier, the slip frequency voltage is rectified and fed to a parallel combination of fixed resistance and chopper. Effective resistance across the terminals A and B is 0 when the chopper is on and R when the chopper is off. The duty ratio of the chopper is varied to control the effective resistance or the average power dissipation in it. The filter inductor reduces the ripple and discontinuity in DC link current, and hence variation of the duty ratio of the chopper varies the effective external resistance. Let us see the expression. So, the duty ratio of the chopper is T on divided by T on plus T off. That is, duty ratio is T on So, when the chopper is off, the power effective resistance between resistance is R. So, power dissipation is I d square into R. Power in the resistance power between the point A and B is P A B is I d square into R, and this power is dissipated in the external resistance when the chopper is off, and that is for a time t off, and in a total time period t, this is the total power dissipated. So, average power dissipated between point P A B, average power dissipation is given by I d square R into T off by T. So, that is I d square into R into 1 minus delta, because T off by T is 1 minus delta. So, you can say the effective resistance between R A B, this is I d square into R A B. So, R A B is 1 minus delta into R, and total rotor circuit resistance per phase is given by this expression, that you can see. You see the rotor current waveform. Rotor current waveform. This is 0, this is pi, and this is 2 pi. This is omega t, this is plus I d, this is minus I d. This is the waveform I 2 A, rotor current in phase A. So, from this rotor current waveform, RMS rotor current, I 2, as you can see from the waveform, it is root over of 2 by 3 into I d. So, as RMS rotor current is this is root over 2 by 3 I d. Now, total power dissipation in external resistance equals to P A B. So, that is 3 I 2 square into R 2, let us write R 2 star equals to, that is I d square into external resistance R into 1 minus delta. So, now in this last expression, substituting I 2 equal to root over of 2 by 3 into I d, you can write R 2 star, the effective external resistance is 0.5 R into 1 minus delta. So, effective external resistance is 0.5 into 1 minus delta into R plus R d. R d is the DC link resistance. Okay. So, and total rotor circuit resistance let us write it as R R T is rotor winding resistance is R 2 plus 0.5 into R d plus 1 minus delta into R per phase. Next, let us discuss a closed loop control scheme. So, the principle is to vary the duty ratio delta. When the duty ratio delta is varied, effective total rotor circuit resistance R R T varies, and hence the speed and torque are varied. So, a closed loop control scheme for that we will discuss. This is the 3-phase supply to the 3-phase induction motor, and rotor terminals are connected to a 3-phase diode bridge rectifier, and output of the diode bridge rectifier is filtered, and so there is a speed sensor for speed feedback. Speed sensor gives the reference, the actual speed measured feedback speed, and this is subtracted from the reference speed, omega m star, and the output, that is the speed error, goes through a speed controller, and speed controller output has to be the current reference, and in this case DC link current reference, but before there should be a current limit control. This is the current limiter, and output of this is the reference current ID star for the DC link. And the actual DC link current is subtracted from the reference current. So, there is a DC link current sensor, and the current error goes through a current controller, and current controller, and this goes to the base drive circuit for the transistor or chopper. And this base drive circuit controls the delta duty ratio of the transistor. So, this is the closed loop control scheme for duty ratio duty ratio control, and it uses inner current control. The current which is the DC link current is the inner loop, and speed loop is the outer loop. So, the static rotor resistance control, the scheme which you have just discussed, has several advantages. So, those advantages we will list. First is smooth and stepless speed control. Fast response, because of the chopper switch, the response is fast. Less maintenance compared to conventional schemes, compact size, simple closed loop control. As you have seen, the closed loop scheme is very simple. And most important, the rotor resistance in all three phases remain balanced. There is no question of unbalance, remain balanced in all operating points. There is no question of unbalance, because the resistance is only in the DC side. So, in conventional methods there can be some unbalance, but in this case there is no unbalance. Okay. So, these are the advantages. There is also one disadvantage. Disadvantage is derating compared to conventional methods of rotor resistance control. Derating is more, that we will discuss after all the method detailed derivation of the derating factor, which we are going to do now. So, let us do the Fourier series expansion. The peak fundamental rotor current equals to I 2 m is I 2 m fundamental, that is 2 into root 3 by pi times the DC link current I d. That can be done. You see this wave form, rotor current wave form which you have just seen, it has quarter wave symmetry, and for quarter wave symmetry B1 is 0 and A1 corresponding to the peak fundamental rotor current, that is 4 by pi integral of I d sin omega t d of omega t. You see from 0 to pi by 6 I d is DC link current is rotor current is 0. So, this is from I d is from pi by 6 to up to pi by 2, and this integration gives 2 into root 3 by pi I d. So, that is the peak fundamental current I, that is equals to A 1. And from this RMS fundamental current, which you denote as I 2 f, that is 1 by root 2 of A 1. So, that is root 6 by pi into I d. So, substituting the relation between I d and I 2, root 6 by pi I d is root over of 3 by 2 into I 2. So, this is 3 by pi into I 2. So, what is the mechanical power? Mechanical power P m is 3 I 2 f square R R t into 1 minus S by S, because effective rotor resistance, total rotor resistance per phase is R R t into 1 minus S by S, corresponding to the mechanical power, and current is only fundamental rotor current I 2 f is responsible for the mechanical power. So, this is the expression for the mechanical power. So, air gap power P g is the mechanical power. Mechanical power is produced by only the fundamental component of the rotor current, but air gap power is mechanical power plus total copper loss. Total copper loss will depend upon the RMS rotor current I 2. So, I 2 square into R T. I 2 is the RMS value of the rotor current. So, air gap power per phase that is P g by 3 is I 2 F square into R R T into 1 minus S by S. This corresponds to mechanical power per phase, plus copper loss per phase, that is I 2 square into R R T. Okay. So, this is I 2 F square R R T into 1 minus S by S plus I 2 square. I 2 is pi by 3 times I 2 F. So, pi by 3 times I 2 F. This is I 2 square into R R T. So, this is I 2 F square into 1 minus S by S plus pi square by 9 into R R T. So, it is pi square by 9 minus 1 into R R T into I 2 F square plus R R T by S into I 2 F square. So, that is R H into I 2 F square plus R F by S into I 2 F square, where R H is given by pi square by 9 minus 1 into R R T, that is pi square by 9 minus 1 into R 2 plus 0.5 R D plus 1 minus delta into R. R H accounts for harmonic, for rotor harmonic copper loss. And R F equals to R R T, that is R 2 plus 0.5 R d plus 1 minus delta into R and R f by S represent mechanical power, mechanical load and fundamental rotor copper loss. So, with this we can draw the equivalent circuit. This is the stator resistance R 1, stator leakage reactance J x 1, magnetizing reactance J x m, rotor reactance referred to stator J x 2 dash. This is R h dash and this is R f dash by S. R h dash equal to A t square into R h and R f dash equals to A t square into R f, and these two R h dash and R f dash are the resistances refer to stator, and A t is the stator to rotor turns ratio. So, this one represents the harmonic loss or harmonic rotor copper loss, and this resistance represents mechanical power and fundamental rotor copper loss. Here only fundamental component of the rotor current contributes to rotor torque and power. So, only the fundamental rotor current is the useful current and total rotor current is more than the fundamental rotor current. So, motor draws more current, but fundamental component which is a part of that is only useful for producing torque and power. So, motor derating is more. So, we have to define the motor derating factor. Motor rating is less than the actual rating what it should have been done, it should have been motor derating factor, and motor derating factor is approximately equal to I 2 f by I 2, fundamental rotor current divided by RMS rotor current, and as you have seen the ratio of I 2 f to I 2 is 3 by pi. So, derating factor is 0.95. So, this is a disadvantage of static rotor resistance control scheme, the motor rating has reduced by 0.5. The rating factor is 0.95. So, apart from fundamental component, there are harmonic components. So, harmonic currents and harmonic MMFs, they give harmonic torques, and harmonic torque has some steady value as well as pulsating value, but these are small. Harmonic torques are negligible. Harmonic torque has a steady state value and pulsating value and pulsating component. And it is negligible, very small. So, this is the analysis of the rotor resistance control scheme. There are many advantages as we have listed. However, there are few only disadvantages. Derating factor is 95%, means motor rating reduces to 95%. Thank you for attention.